we stopped at a point where we basically know how to write a character table. We kind of know how to get the invariant functions, some basic invariant functions. And the question now is, okay, how can I use this knowledge to derive physical properties? And this is what we're going to do today on a couple of examples, and then I will show you some very recent work we did on the spin torsion scheme area, conductivity tensor on a certain C3 point group, which is my favorite point group at the moment. So let's set the problem. So consider, for example, and again I'm very closely following Dresselhaus' book here, that we have a crystal with bands and stuff like that. It's okay. And we shine light on the crystal, so we have this interaction. Remember that, this is something I mentioned very quickly last time. And what we'd like to know is that, let's start, we basically would like to know how this interaction Hamiltonian allows transition from states of a given representations to states of another one. Okay, so concretely, you have different bands, you shine light, polarized or linearly polarized, doesn't really matter here. Well, we'll see actually. You shine light on the system, and of course you will allow, this will enable transition between bands. And those bands, they are characterized by their representation. Okay, this is why, if you look at band structures, you will have these gamma 1, gamma 2, gamma 3 that are written on the bands. If you're delta 1, delta 2, delta 2 prime bands, they all refer to specific representations. Okay, so that's the problem we have. And of course, what you see here is that, well, okay, we're going to need the representation for the initial states, the representation of the final states, and the representation of the interaction. So we're going to have to combine 3 representations. The way we're going to do that is that we're just going to focus on this product here. We'll say, okay, let's start with a state with presentation gamma I, and let's see how, when I apply this Hamiltonian on psi, so Hamiltonian with, let's say this is gamma 1, this is gamma 2, how the product between this representation and this representation generates all the representations. Okay? In other words, once I have written this product, the representation of this full product becomes reducible. Okay? So these are all irreducible representations of the crystal. And when I make this product, I create this product, I'm going to have a product of representation, which is itself a reducible representation. Then I need to decompose it. Okay? This is something that we have already seen. So I will have a product of representation, I, J. So these are all irreducible representation of my crystal. And I will need to write them as a sum. No, I need to change my indices. Okay, here a sum of the other irreducible representation of my system. So this is the first step. We'll see what it means physically. Of course, there's a profound physical meaning. So of course, there's a theory behind that tells you that it is possible to express a product of representation into a sum of irreducible representations. So I will go fast on that, but I don't think this is useful for us as practitioners. What matters is that what we've been doing since the beginning is we've been trying to avoid using matrices, using realistic or concrete matrix representations of our one group representation. There's a lot of representation in the same sentence. I apologize for that. So the way we're going to do that, it turns out that this kind of relation is valid at the representation level, at the abstract level. It's also valid at the character level. And that is very nice. So basically, the character of a product is the product of the characters. Once you understand that, which can be kind of natural in a sense, then it's very powerful, and we can actually build up this expansion. So let me just jump directly on the rule. if I take a particular symmetry operation R, because of course this is valid for at the representation level, so you know that the representation itself has a number of characters for each of the symmetry classes of my system. Okay, that's a global level if you wish. And concretely at the local level, what I can say is that if I pick a certain symmetry, let's say a C3 symmetry, then the product of the character of this symmetry of two different representations, let's say this is my gamma I, let's just put it this way, let's say gamma I, gamma J, can be decomposed into, I'm just translating this expression here, the sum, this would be, yeah, okay. So let's put the, this would be gamma K, for example. That would be the K, actually. Yeah, okay, gamma K. It's more explicit. That would be gamma I, gamma J, gamma K. I have to write I, J, K, but this is, this way we remember that we are talking about the character of a given representation time the character of, well, the representation over which we project. So this looks very much like a vector decomposition in a sense. Well, except that this is not a scalar product. But anyway, now what we care is about this coefficient here. Okay. So this coefficient, again, I'm just throwing the formula, is given by this formula. We're just going to deal with groups that are that have real characters, so we don't care about the complex conjugates. But basically, we will pick for every. Well, I mean, basically, this is the dimensionality of the class, and this is a product of the three characters. So you know we have three representations. We have the product of I and J. We have I and we have J. We have three representations. So we're going to take for each transformation the product of the three characters multiplied by the dimensionality of this particular representation and sum everything. And that will give us the coefficient. Okay? So let's do that. This is still abstract, but you know, it's going to work. I will probably work on, let me see. I will work directly on this one. So, concretely, as I said, I take my crystal. It's I think it's a TD crystal. It's a TD or it's an OH? I think it's TD. Anyway, so it's I think it's a tetragonal crystal. Doesn't matter. This table. It's a very complex table. A lot of numbers, a lot of classes. You see that there are actually 48 operations. And what we're going to say is that we start, for example, with the state, a certain state that is at T to G. So T to G is here. Okay? It means that we want to excite a state that has this typical function. So typically you take a dxy state, okay, and you shine light on your dxy state. And the question is, where is this dxy state? D, the d orbital. No? Where does it go? So we have, in this case, if I make the correspondence, we have a T to G. I will write it here, actually, it will make more sense. So this is the state over which we apply our excitation. And our excitation is P dot A. So A is my vector potential, that's fine. What I care about is P. So let's say P is a polar vector. So we just look at our table, and the polar vector has which representation? It's super obvious, but I want you guys to get engaged. T, U1, 1U, sorry. Okay, X, Y, Z. It's a polar vector. So our excitation has a T1U symmetry. Representation, sorry. So then my product, so when I apply this excitation on my state, I'm going to have this product. Okay? So what I want now is to write this product, to decompose it over all the other representations of my system. And that will tell me where my state can go. So I'm going to have selection rules, optical selection rules, just by looking at my character table. It doesn't tell me how much it works, just tell me that it works. Yeah?
Why are we only thinking about P and not the product of P and A?
Because, well, we are... Now, P is your momentum. So actually, A will tell you whether you only select PX, PY, or PZ. We basically tell you the polarization of light. Okay. So if you say, okay, I'm only taking PX, that's fine. PX is still there. If you're only taking PY, this is working the same way. If you actually have circular polarization, it's going to be a combination of that. So we still stay at the T1U level. Okay. Okay, so our perturbation is here, and our initial state is here. Okay. So the first thing we can do is to write the series of characters for the product of those two representations. Okay. So then we can have a series of characters, and I will actually done the work here yesterday. So this is character of T1U, character of T2J, and character of the product. Okay? Now what we want is simply to find those coefficients. It turned out that, I mean, I didn't do it for everything, because, you know, we have, I don't know how many classes. We have something like 8, or no, we have 12 classes. I don't remember. You have a lot of classes. So I just take the one that are non-zero. You actually should do the calculation, but as you see, this is simply a product. It's super simple to calculate. It takes really like 2 lines in your favorite coding language, maybe 3. So I'm just looking at, I mean, it turns out that the only representation that you can decompose this product on are A2U, EU, T1U, and T2U. And I'm just looking at the coefficient as an example. I'm just going to calculate this one. Okay? So I apply my formula. H here is the number of symmetries of my point group. So I have 48. So this is divided by 48. No, 48 to 24. No, 24, 48. And then I simply need to do the calculation. So let's take the first. Let me see, we have all these things here. So I will start with the first one. So E has a dimensionality of 1. And I multiply the 3 characters of this one, and the A2U character, the one on which I want to decompose my product. Okay. So that would be, oh yeah, okay, I couldn't write it. This guy, so that would be -1 times, I'm sorry, I should have probably done it. 2U is here, 1. Okay? So then you have, oh yes, it's a 3, excuse me, no, it's an E representation, sorry. It's a E transformation, so that would be, I have 1 here, 3, 3, and I have dimensionality of 1. So that would be 1 times 1 times 3 times 3 times 1. Okay? Then the next one, I should do -1 times -1 times 1 times 3. Because the dimensionality is 3. And so on and so forth. It's very simple. Very long, but very simple. And at the end of the day, what you get is 1. That's for one coefficient. So when you do that for every single coefficient, you end up with that. So this tells you that if you take a T2G state, so a dxy, dyz, dzx, and you shine light on it, then this state can can transform into one of those 4 states. It doesn't tell you how much. It doesn't tell you more than that. But it tells you that at least this is working this way. So you actually can basically simplify, I mean, you restrict the domain on which you work. Okay? You have any questions here? Yeah.
So these states are the byproduct of the T2G state, right?
Yeah.
These new states are the bipolar of the T2G state, right?
And what?
The bipolar. I mean, are they coming from the T2G state, or are they just separate states?
Oh, they're completely separate states.
Okay.
No, they are all, so all those representations are orthogonal to each other, right? So it means that a state in this representation is orthogonal to a state in this representation. So that from the band point of view, these are all different bands around gamma point. Because, okay, I'm not working with a little group. So the little group here would be at around gamma point. That would be exactly this group. Okay. So if you just think in terms of the gamma point excitation, those guys are just different bands. So you go from, let's say, band T2G to band, I don't know, A1U, for example. Okay. So it tells you that any transition from, just want to show, yeah, from T2G to T1G is forbidden. Which kind of makes sense because, you know, G and U, they actually refer to the parity. So the G means you have an odd parity, U means that you have, no, let's see what opposite. No, G is you have an even parity. That's a German, so I don't know if there's German speaking people here, but I haven't learned my German. So this is even, this is odd. Okay? So now let's go back to our the problem we left yesterday, which is to derive our Hamiltonian. So it's a bit simpler. We have not as many representations to deal with. So we have our D3. We have A1, A2, E. That's our representation. Our character table, and we have the actual functions that obey or fall into these particular, the different representation. And what I want to do is to write a Hamiltonian. So the Hamiltonian is a number, it's a scalar. So it should transform as an A1. Okay? So what we want is to find combinations of those different terms that give me an A1. So as I was mentioning, the obvious functions are x squared plus y squared and z squared, because they already fall in A1. So this is going to give me my my kinetic term, which is an isotropic, because it's a D3. And then what I want is to look at the spin-orbit coupling. So I want to have terms that are at least, well, that are linear, because it's a spin 1/2, so linear, in an actual vector. Okay, so we have terms that are RZ and terms like that. So what we did last time is that we said, well, if I multiply those two functions here, it means that the characters of the product of A2 by itself will simply be 1, 1, 1. Okay? And you see automatically that this is an irreducible representation. In this particular case, A2 times A2 is equal to A1. Okay? So that's my decomposition. And this I don't need to do any calculation because I just see it automatically. I multiply the characters by themselves, and then I have 1, 1, 1. And this character distribution is unique. Okay? If you have 1, 1, 1, it is an A1 representation. There's no other choice. Okay, so this is easy. I'm going to have a term that is Pz sigma z. If you think in terms of band structure, I'm trying to make connection with what Barry was mentioning. We are in the little group of gamma, so we are around gamma. Okay, we're always around gamma equals 0. The k equals 0. So then we have a Dirac cone emerging. Okay, now let's look at this, the product between this guy and this guy. Well, I could actually consider this product. I could consider this one. I could consider this one. Okay, because I want to. I'm building my minimal Hamiltonian. I will just take the product between those guys. But it's I think very important to keep in mind that this product here and this one here, these are also allowed from the symmetry perspective. Okay, so if I do that, then I have an E square, right? An E cross E. So now I have to decompose. Why? Because E has a dimension of 2, right? So two-dimensional representation. If I multiply E by E, I'm going to have a 4-dimensional representation. And this tells you that because this 4-dimensional representation is larger, has a larger dimension than the largest dimension of the irreducible representation, basically 4 is larger than 2, it means that I need to decompose it. It is a reducible representation. So I'm going to find my alphas. So I would say that I can write this reducible representation into A1 into E. And these are the explicit coefficients. So let's do one of them. So if I look at the coefficient alpha 1, the number of operations is a 6, right? You have 1E, 1 identity, 2 C3 rotation, and 3 C2. So this is 1 over 6. Then I'm going to have, let's see, I'm going to have, yes, yeah, okay. I'm going to have this guy times, so this guy times A1 times the dimensionality. So 1 times 1 times 4, give me that. Then 1 times 1 times 2, here, 1 times 1 times 2, and then 3 times 1 times 0. So this gives me 1, and so on and so forth. So I end up with, didn't write it. I end up with this decomposition. A1 plus A2 plus E. Now let's work. No, this means that when I will create the product, I have to, so the product between xy and rx, ry, I'm going to have different terms. I'm going to actually 4 terms. This is what we did yesterday. Okay, we have this rxx plus ry plus then all the possible combinations. If you remember Oleg's presentation from yesterday, when he was actually expanding in the in the second order gradient with the d alpha, n alpha, d beta, n beta, he had exactly the same kind of reasoning. And he actually had to look at all the alphas and betas possible. So d alpha, n alpha, d beta, n beta, and d alpha, n beta, d beta, n alpha, and so on and so forth. We're doing the same thing here. So we're just varying the different, and just considering all the possible combinations. And it turned out that where Rx, so I mentioned last time, I'm just going to repeat it again. Remember that you see in this particular space group, because there is no mirror symmetry, the actual vector and polar vector behave the same way. They're exactly the same, well, they behave the same way, which means that the Rx x plus Ry y has the same behavior as the x squared plus y squared from the symmetry perspective. So it means that this one follows into A1. The Rx y minus Ryx has the same behavior as, let me see. Oh, no, what am I doing? Yeah. Okay, this one I believe is actually, no, it doesn't have a similar behavior because this gives 0 otherwise. It turned out that this one I think falls into A2, and those guys must actually be together. Okay. So this one falls into A1. If you look at this structure here, this looks very much like this one. Okay, it's x squared minus y squared xy. So this falls into A2E, then this one must fall into A2. Okay? And the minus sign here, the fact that if you switch the variables, you get a minus sign, give you this -1 character. So that's why this one falls into A2. So the one we want is this one. Then I complete my Hamiltonian. Yeah?
I have a question. Can you repeat your argument why the Rx behave as X?
Oh, because if I look at the character table, they just behave the same. They fall into the same representation. We see that for the C3V symmetry, this is not the case. The RZ and Z do not behave the same way because there's a mirror symmetry, And then the Z component switches sign inside the mirror. And so the RZ component switches sign inside the mirror. This way, sorry. And the Z component does not switch sign. Okay? But here, it works the same way.
Then how do you know that RXY minus RYX belong to A2?
So you have two ways. Either you actually perform the transformations on that. And what I would do is that if I exchange the signs here, I mean the indices here, I'm going to have a minus sign coming here. So it's a function that bears some odd parity. And the only odd parity I have is here. Because when you do this rotation, you basically exchange x and y, and this is what you. So that would be one argument. The other argument, which for me is I think the easiest, is to say I know that my decomposition is A1, A2, E. I know A1, I know E, so this must be A2. You have to put it somewhere. So then you end up with this Hamiltonian, which is typically an anisotropic wave curve. Okay. Is there any question here? Okay, now we go all the way. So let's now practice and let's do some, let's develop some formulas for physically relevant effect. So we're not going to do everything, sorry, not everything. But I would like to just give you the general ideas. So we're going to consider actually just 3 of those effects. We have started to work on that too. But let me just walk you through that. So if you consider the linear conductivity tensor, and this is something that Jakub was mentioning. So what Jakub does is that he actually takes the actual operation, the actual matrices. Okay, and he applies these matrices on these transformations on the tensor response. What we do is a bit different, but of course it boils down to the same thing, is that we just expand our polar vector, because the current is a polar vector, in terms of those different coefficients, and those coefficients are taken from the table. Okay? So we have invariant functions, and we just combine all the possible invariant functions to create a polar vector. So at the first order, well, the polar vector must be proportional to the polar vector of the electric field. But you could also say, hey, what could I have a term that is proportional to the magnetization as well as the electrical field? So we know that what this is, right? This is the Hall effect. Okay? So could we have a Hall effect? We know that Hall effect is permitted. There's no spin-orbit coupling physics here. There's no microscopic reading. It's purely symmetrical. And what we'll see that if we allow this term to exist, then we have an actual vector here. So it turned out that this one must behave like an actual vector, which is strange because it's a polar vector. So we'll see how it works. We basically have to engineer our electric field so that it behaves like a polar vector. And I'll show you how it works. You could also go to the next order. So what is that? What is this kind of effect? Second order, so first order in electric field, so it's all linear, but second order in magnetization. Sorry? So it's an isotropic magnetoresistance and planar Hall effect. And they are two sides of the same coin. So we have here regular conductance, Hall conductance, planar Hall effect / AMR. We can have actually more. You can go even beyond that. For the Joyce-Skimmer interaction, we're going to do the same thing, but now we're going to be looking for a scatter. So an A1 or a gamma 1 representation, because that's an energy term, and the energy, of course, should be completely invariant upon all the operations of the system. We will assume that we only have, well, in this particular case, I will show you some cases where we have more than 2 magnetic components, but in the expansion here, the first order should be m, m gradient m. So we have two actual vectors and one polar vector. You could also imagine two polar vector and two actual vectors, and so on and so forth. Okay. There is a subtlety here that I will mention later, because you don't know where to put the gradient. Should you put it before, in the middle, after? Doesn't really make sense. But we're going to look at the spin-orbit torque. So spin-orbit torque. So we're not going to look at the torque. We are going to look at the field. Okay, the field is an actual vector, and it's an actual vector that is proportional to the electric field. So we have a polar vector here, an actual vector here. So we have the same problem as here. This field, which is itself the xyz is a polar vector. So we will have to find a way to write the xyz in an actual manner. Because this is an actual field, so this must be the form of an actual field. And then, we can go first order, second order, and so on. And this is all the same business. So what is interesting here is that you are not, for the spin torque expert in the room, we don't, when you do the macroscopic calculation of the spin-orbit torque, you actually have two components, the field-like torque and the damping-like torque. That's very simple. And the field-like torque is usually attributed to Fermi surface, Fermi surface term of the Kubo formula, and the damping torque is attributed to the Fermi C term of the Kubo formula. And they have different symmetries with respect to the magnetization. This doesn't care. This just tells you, I want a term that does not depend on magnetization, that is first order magnetization, second order, and so on. Now, from the macroscopic physics point of view, this guy must be Fermi surface, because it's even in magnetization. This one must be Fermi C. And we can verify that when you actually do the macroscopic calculation. Now, the last thing I wanted to mention, because I think this analysis is super powerful for this particular case, is a nonlinear Hall effect. Have you heard about that? I know you did. You heard about the nonlinear? So basically, you know that anomalous Hall effect, take a ferromagnetic material, you send a current, you get, if you have spin recoupling, you get a transverse Hall effect. Okay? Now, what if there is no magnetization? I'm not even talking about antiferromagnet, like no magnetization whatsoever. Then of course you'd say, well, at the first order, I have no magnetization, so I cannot have any transverse effect because my current must behave as a polar vector. Must be an isotropic, but there's no Hall effect. There's no transverse current. However, at the second order, if you break inversion symmetry, then you actually have a Hall effect. And this is allowed by the crystal symmetry of your system. The physics behind it is that of course, you have to break the inversion symmetry in the plane, in fact, not perpendicular. It's not a Rashba effect, and it's an in-plane inversion symmetry breaking, like typically what you have in tungsten deuterium, for example. Now, you see, if you look at the shape here, there's a triangle here and a triangle here, so there is no inversion symmetry breaking in this plane. So you break it. So when you send a current this way, you are actually going to create an orbital magnetization perpendicular to the plane, which is a non-equilibrium orbital magnetization. So you do create magnetization, but out of equilibrium at the first order in the electric field. Then at the second order, the electron that come after, if you want, the secondary electron, they come, and there is already magnetization here that is first order in the electric field. So there is a Hall effect. So there is a Hall effect at the second order. And if you do not break inversion symmetry, there is third order Hall effect. And you can go on like that. One thing, because nobody asked the question about Onsager reciprocity. Onsager reciprocity works in the linear regime, not in the nonlinear regime. In the nonlinear regime, there is no way, you cannot impose Onsager reciprocity. It doesn't make sense at the second order on beyond that. Okay? So that's what we're going to do. Okay, so I will take, to be frank, we have done it for one material, because there was some good reason for that. We had a collaborator, I told you that a couple of days ago, a collaborator that came with some interesting experimental results, and we tried to understand it by playing with the with the symmetries, and then we came to the point group, and then we came to this invariant theory. So I'm just going to focus here on the C3V minimal model. And try to, I will actually start by the microscopic physics. Okay. For macroscopic, so what we have it's a C3V crystal. It's a L11 crystal with inversion symmetry breaking at the interface. So the minimal model we can build is an hexagonal lattice, and if you want to, so that would be of course you're going to have the hexagonal symmetry. But if you want to get the C3V symmetry, of course there is inversion symmetry breaking in the plane. That's Rashba, this is easy. But to get the 3V, you need a mirror symmetry and a 3-4 rotation. So that's why I put those atoms here. Okay, that enforce the mirror symmetry and the 3-4 rotation. So what we can do is look at the character table. This is not what we did because it was the early days of this work. So what we did is that I was playing with my hands, trying to see what kind of spin-orbit coupling we can have. So of course there is the Rashba spin-orbit coupling coming from the inversion symmetry. And from the microscopic perspective, you could say, well, if I jump from here to here, I can go this way. So if you have no atoms, okay, if you have no red atoms, you just have the gray ones, you can jump from here to here either straight or through this atom, and you create an angular momentum, let's say up, and through this atom. So you create an angular momentum down. So they compensate. Now, if you add this red atom here, then this angular momentum here and here, they do not compensate. Okay? So this creates a Rashba effect, if you want. It's the same idea as the Rashba effect, the perpendicular to the plane. And now when you do the math, the nearest neighbor is here, the next nearest neighbor is here, and what you end up with is a cubic term. Okay, so it's perpendicular to the plane, sigma z, and is cubic in K, with this strange threefold symmetry. And that is directly coming out of the macroscopic physics. And then we realized that Yang Fu, who has done so much things, so many impressive work, actually has done this analysis, the symmetry analysis, in the case of topological insulators. You know? And I mean, his idea was, if you take a topological insulator, you know that you have a direct gap. Probably heard about that already. But if you go high in energy, you actually end up with, okay, I'm going to do it the other way because otherwise I will not be able to do it. Yeah, okay, you can have this kind of hexagonal warping. Okay, you go from a circular Fermi surface to a star-like Fermi surface. Now, of course, our interest was not in the topological, I mean, in the Dirac codes. So you actually take this Hamiltonian, you implement some parameters. We actually we don't use this free electron model, we actually do the time binding model, which has many advantages. It's much more realistic, first of all. Of course, analytically it's not super tractable, but it doesn't matter. It's super easy to calculate numerically. And most importantly, well, you actually end up with some very neat and physically relevant Fermi surfaces. So here the magnetization is this way. You see that there is a shift of the Fermi surface, and that's because of, if I put the magnetization here, I have a shift. That's because I have Rashba. If I do not have spin-orbit coupling, right, putting the magnetization up, down, on any other direction doesn't matter. But because of the Rashba spin-orbit coupling, basically I impose the magnetization to be along the x direction, so the spin will be along the x, which means that the momentum will be shifted along the y. So you have this small shift in the Fermi surface. So that's your Fermi surface when you're at the bottom of the band, nicely circular. So basically, if you calculate your stuff, this one does not do anything because it's cubic, so it's much, much smaller. And then when you increase the Fermi level, okay, and especially in this region here, you start having some warping, some very progressive warping. And the red color here is when there is the cubic spin-orbit coupling. So there is some kind of distortion of your Fermi surface. And that's physically, that's super important because this warping here is really coming from, I mean, yeah, this you cannot see that here. Yeah, I should have put the magnetization perpendicular. That would have been more clear. Anyway, in this region only this cubic term will act and will. So all the interesting C3V, I mean all the interesting effects that belong to the C3V or that are specific to the C3V crystal, they will appear in this regime. Right? When you are at the bottom of the band, well, basically the C3, the block state doesn't see the C3V symmetry. Okay, that's a very important notion. So, yeah.
About this figure E, so it is like I mean 2D projected heavy surface of the 3D surface? Or
It's a 2D system.
2D system. So,
Yeah.
I mean, if you see this heavy surface, is it not considered as C6 instead of C3?
It actually no, because well, it's not easy to see because we took because that's a Polish paper, so we don't want to put some dramatic parameters. But if you look at that, this guy here is not this. I mean, for a C6, you should actually have the same shift, and this is not, they are not exactly the same. Yeah, it's not very clear here. I apologize. I should have enforced. I mean, taken a larger parameter, and that would have been more clear. Yeah. But you're right. I mean, yeah, it actually depends where they put the magnetization to. Right? So here, where the magnetization is here. So on top of the, I mean, there is also a shift coming from that. So it's not very clear. But what I think is important to keep in mind is that when you have a crystal with a certain symmetry, your block state does not necessarily pick the symmetry. Okay. So the symmetry is here, it's a crystal, so you have all this representation, all this business. But well, if it turns out that I don't know, let's take something very simple. Let's take this hexagonal symmetry here. Oh well, it's not hexagonal. Here, hexagonal symmetry, hexagonal crystal. Well, if the wavelength of the crystal is of this order, well, that's probably too short. That's too short, but basically, if the wavelength of your block state is of the order of the lattice parameter, then you expect the block state to see, the wave function will basically scatter on the lattice, and you will basically imprint the symmetry of the crystal on the block state, because that's the only way the block state can survive. But if the wavelength is very long, doesn't care. This works as an effective medium. So concretely, what it means that if you have, that's exactly what I was mentioning here. At the bottom of the band, we are at small k, so very long wavelengths. So we don't have, so it's a circular symmetry. We don't see the crystal. Okay, it exists, but the block state doesn't see it. And when you get higher in energy, then the wavelength decreases. The k vector increases, and then you start imprinting the symmetries on your block state. Okay? Okay, so let's look at our character table. So we take the C3V character table, which we have it here. At this stage, we don't care really about, well, okay, we keep in mind, but so we just look at the linear effect, and we're going to focus on the current. Okay? So we have those, usually in the literature, they only give you that. They may give you the quadratic term for the polar vector, but very rarely for the actual vector. So you have to do it yourself. And it's not like the Bilbao table. It is not available. We were actually looking at that with Jakub, and this is, I mean, you have to do it. It's not a big deal for the magnetization. It's, especially in those cases, you just know that as soon as there is a mirror symmetry, then you have to be careful. That's it. So we actually look at all these symmetries, and at the quadratic level we have this thing, and at the cubic level we have those things. So they look horrible, but it's not too bad, because you see that this vector, for example, this two-dimensional vector, it's basically this vector multiplied by z, because z is in the A1 representation. Okay? Yeah, we have no inversion symmetry. Huh? So there is no operation that reverses z. Right? Z stays out of the plane. we would have a C3H, then we would have a mirror symmetry, and Z might not belong to A1. But here Z belongs to A1, that's fine. Yeah, this is the difference between MZ and Z, right? You have this free-fall rotation. So their character for the free-fall rotation is 1, both of them. But they actually behave, we have opposite parity for the mirror symmetry, because you have a mirror symmetry that is perpendicular to the plane. So the Z component is not modified, but the MZ component switches, because it's an actual vector. So this is the kind of thing that we have to consider, and you see that actually this vector here is just this one multiplied by Z. This vector here is just the xy multiplied by Z squared, and so on and so forth. So there is no, I mean, the only interesting elements that are a little bit different from just the trivial combinations here are those guys. This one, this one, this one, this one. Okay, and these elements, I write them with the vector and so the vector components. But if you write them with polar angles, azimuthal angles, this is going to be cosine 3 phi, sinus cosine 3 phi, sinus 3 phi. So you really have this threefold symmetry. Okay, that is embedded into these invariant functions, and all the rest is rather trivial. So what we want to do now is to combine all these different functions to get our current. So the current is a polar vector. So it means that it should transform, the current vector should transform as Z and XY. So the Z component of the current should be in A1, and the XY component of the current should be in E, sorry. Okay? It turned out that we don't care about the Z direction because we have a two-dimensional system. We never send the current perpendicular. So makes our life a little bit easier. And then we start. So basically, if we look at the first order in the electric field, the current must transform like the electric field at the first order. The electric field is here, the same representation as the current. So it simply means that your current must be, yeah, I know it's ugly. Yeah, you have to follow me here. At the first order, the current must be proportional to the electric field. Okay? Now, let's look at the first order in magnetization. There is one interesting subtlety here, because what we say is that we want, so we have our current, let's say this is Gx, our current here, which is proportional now to magnetization component, I don't know, I, and electric field J, components. Okay, these are the components. So Mx, Ex, My, Ey, something like that. Well, this M here is an actual vector. Okay? So, so we basically have different ways. We can actually combine Mz with an electric field. So combine Mz with, well, we don't have a choice, we have to combine Mz with that. Actually, we always, I mean, the electric field is always here. So we can combine Mz with this, or Mx, My with this. Okay? So we have two possibilities. We have two kind of constructions. We have the Mz multiplied by the Ex, Ey, and we have the Mx, My multiplied by the Ex, Ey. So this one looks very much like what we did, which we just did like 10 minutes ago when we were working on the Hamiltonian. Okay, Rx, X, and so on. This one is a bit different. Because what we want, well, we know that this guy is an actual vector. This guy, well, in this form, if I take Ex along X, if I write it like Ex along X plus Ey along Y, this one is a polar vector. So I want a first order term in the electric field, but I don't want this one. So then you can think, well, I have four other possibilities, right? I have Ex along Y and Ey along X, for example. and so on and so forth. It turned out that the one that is anti-symmetric, that is an actual vector, the one that transforms like an actual vector is Z cross E. So this one, you can verify, is transformed as an actual vector, and if I make the product of those two guys, I will have a polar vector. So basically what I just said is that first order, I have the electric field, that's fine. Polar, polar. Second order, I have the Hall effect. Actual, we give you a polar. But this is not the only thing. I could also now consider that. And again, I'm going to have E square representation. Okay, so I have different forms of effect. I have mx ex plus my ey, mx ey plus my dx, and then I also have the minuses. So I have exactly the same rationale as what I did for the D3 group. I have to do it again now, and pick only the term that it belongs to E. So as I said, if you start combining everything, you have a term that belongs to A1, a term that belongs to A2, and a term that belongs to E. I want the one that belongs to E because that's an actual vector. And that's this one. Okay. Now there are other combinations, the one that belong to A1 and A2. And it turns out that they are present in my system, but only if I multiply it by NZ and take a Z cross. Then if I move on to cubic, that's actually interesting because once I have this term here, just focus on this one. Anything here that belongs to A1 exists. So these components and these components also exist. So at the first order, I mean, my current should be 1 plus something with mx squared plus my squared. Well, m is the norm of m is 1, so I will take so 1 plus mz squared, for example, plus this one here. So this gives you automatically an anisotropic component. So this is an isotropic magnetoresistance. This one here. And of course, the Hall effect also has an isotropy. Because you look at, so Mz belongs to A2, so any combination of the magnetization components that belong to N2 will also be valid. So at the third order, we have this one. And if you go to fourth, 5, and fifth order, and so on and so forth, this is still, you can still actually expand what is inside this this coefficient here. It is still Hall effect, but with some anisotropies. Okay. Then we can also look at the quadratic terms. So we actually combine those guys. We can also combine those guys. And when we do that, we end up with a term that is a bit strange, but that depends on the magnetization square. It's even in magnetization. This one is AMR, so this AMR and Palmer Hall effect. Okay. So it's a bit different. And there is an AMR here, and there is an isotropic conductivity. It's not exactly the same thing. Although you have some correspondence here. So. Do you have any questions about that? Yeah.
So could you repeat again how the terms from A2 fit into sound?
So the A2 term here. So A2 is a 1, 1, minus 1. So if you want to have a E here, you have to combine it with another actual vector actually to have the, you have to combine this guy and this guy because we want the electric field. So all the terms here must be proportional to that. Okay? All the terms, they are proportional to components of the electrical electric field. But the component can be Ex along X, Ey along Y. They can also be Ex along Y, Ey along X. It doesn't tell you exactly in which direction they are. It just tells you that you need both terms. both components. So the way it works is that you realize that this combination works. So you will basically look at mz times all the possible combinations. So we have ex plus ey. We have ex minus ey. We have ex y plus eyx. And we have ex y minus eyx. Yes, here. Okay, these are all the possible combinations. And now we just look at when I take this. So if I just pick this one is a polar vector. So this is my current. Now it turned out that then I'm looking at the different components, and actually the only one that gives you a polar vector at the end of the day is this guy times this one. Okay. Yeah. Okay, so blah blah blah. Yeah, so what is interesting here, so as I said, we have some anisotropic conductivity, an isotropic Hall effect, planar Hall effect, anomalous Hall effect. This one is interesting because this is something that we were not expecting. This is actually a Hall effect but in plane. So that's very unusual. Because normally you would expect that to have planar Hall effect. Let me see how it works. So planar Hall effect, so I mean you have two kinds of Hall effect, right? You have the anomalous Hall effect that switches sign when you change the magnetization direction, in the MZ direction, that's here. You have the planar Hall effect that is even in magnetization. So if I change the magnetization direction, I do not change the Hall effect. That's planar. So this is intrinsic, extrinsic. So Fermi sea, Fermi surface. And we actually find another effect that is, it's actually a transverse current, right? If you send the current along Y, you end up with a, sorry, the electric field along Y, you end up with a current along X. So this is the Hall effect. But this one is odd in magnetization and does not depend on the out-of-plane magnetization. It just depends on the in-plane magnetization. So this is very unusual. Of course, you can calculate it because it's odd in magnetization. It's actually coming from the barrier curvature. So I would say it belongs to the same class of Hall effect, but it's very specific to the C3V materials. I don't like to use chirality on topology at every single slide, but it's actually a chiral effect. So chirality means inversion symmetry breaking plus magnetization. Okay? If you have magnetization and inversion symmetry breaking, you can have a chirality. So this guy will be different from this guy. And that's exactly the origin of this effect. Because we have inversion symmetry breaking, so C3 point group, plus magnetization. So when you actually rotate the magnetization, you actually see this kind of effect. So we actually did this analysis because we had this experiment again from Jingzheng, where he was observing some shifts that he could not understand, and then we realized that this is actually coming from that. Yeah, this chiral Hall effect is here, and I'm sorry, I made a mistake. The chiral Hall effect is here because it depends on MZ. Yeah, so chirality is magnetization plus inversion symmetry breaking, so we have an effect that is proportional to MZ and X. So it's different from the anomalous Hall effect. The planar Hall effect, sorry. And then we on top of that have an in-plane Hall effect, which is kind of the counterpart of the planar Hall effect. So we basically add two new, Pierre doesn't like it, but it's new. So two new Hall effects that are simply coming from the symmetries. So of course, if you have, there was some study in copper tin sulfide, right? I mean, this waves, this magnetic wave semi metal, when they observe this kind of effect. But you don't need wave semi metal. It works for your copper platinum, cobalt platinum bilayer. Okay, now we move to the Jaussian-Skimmer interaction. So we can do the same thing, And well, again, now it's kind of easier actually, because the previous one you want a polar vector, so you have to verify that the vector you get is always polar. Here you don't care, you just want an A1 representation. So A1 is very easy. If you take, so what we want something that is even in magnetization, so we want 2 magnetic components at least. Can actually go for 4, for example. And we want at least 1 gradient. We can have more, it's fine. We actually have, I went up to the 3rd order. So if you go to the 2nd order, you're going to have some anisotropic exchange. I don't care about that. I just want to look at the odd order in gradient, because that's Josephson-Skimmer interaction. That's the anti-symmetric exchange. So we have the MZ here, that is A2. And we want the MZ to be combined with a gradient, spatial gradient, and magnetization. So we want MZ to be combined with that. So as I said, well, you go back to here. Gradient. No, no. You go back to this. Sorry, to this. We know that we have one combination that gives you A1, another combination gives you A2, and a 3rd combination gives you E. So we have A2 here. So we need a combination that is also A2. And the combination that is A2 is gradient dot M. This one behaves like an A2. So we have MZ times that. This belongs to the Josephson-Skimmer interaction. And then we can go on. So if it works for MZ, it should also work for that. And we have this contribution here. And so on and so forth. Okay. So we have this, anyway, so I will not do everything step by step, but so you actually have those different contributions. What is super important, I really want to emphasize that, is that here, it's a gradient expansion. So you are completely allowed to make any combinations you want. But then you come with the physics interpretation. If I am allowed to write my energy this way, it means that I have considered that the gradients are very small. So I have smooth textures. So this is not valid if I start having some sharp textures. And this matters here in this particular case, because you see that the Josephson-Skimmer interaction you get, actually this, let's see, these 3 guys do not do anything interesting in the system. They are not Lifshitz invariant. If they are not Lifshitz invariant, it means that they do not stabilize chiral structures. If they exist, they do not stabilize chiral structures. So they are not Josephson-Skimmer per se. You can go beyond that. You can have some 3rd order gradients. Now you see that the gradient is a bit complex, because again, it's coming from, so mz squared here is coming from this guy. Okay, so this guy times this one, for example, mz squared. But this still does not stabilize chiral structures. So if you, it turned out that, okay, I will say, so keep that in mind, right? That's somewhere. That doesn't stabilize chiral structures in the long range approximation. Now the last thing I want to talk about is the spin torque. So I'm just giving you the, so you have 3 components, x, y, z, hx, hy, sd. So hx, hy should be here, hz should be here. Okay, then do it again. So we're not entering all the details. We have an axial vector here, we have a polar vector here. So if we have a polar vector, so we have an axial vector, it means that this guy behaves like this one. So we simply need to multiply it by all the A1 possibilities. So we have this guy plus the m squared plus, so basically it's a field-like torque. This is a Rashba torque with an isotropy. That's how you could interpret it. There is the damping-like torque with some anisotropy too. Okay, fine. What is interesting is that we have more. So we say from the dynamical point of view, those 2 guys don't do much. There is an isotropy, so if you look at the details of the dynamics, you will see that the precession will be different, and the resonant frequency might be modified by those anisotropies, but they do not fundamentally change the dynamics. What is interesting is actually all the 3 other terms. The most important one is what we call the 3M torque, because it's really coming from the 3M symmetry, the C3V symmetry. I mean, I will not enter into details. I just want to show you how it impacts, because I think this one is very important. So we have a torque. If you remember, you might not remember it, but I will put the slide online. If you remember the form of the current, you know, we have current that are linear. So we have this contribution that is linear in magnetization. And actually the invariant form of the 3M torque has the same kind of combinations. Okay? We have the MYEX plus MXEY and MXEX minus MYEY. So you retrieve those invariants and you recover them. If you go even beyond that, you have a planar hole torque. We call it planar hole because the magnetization dependence looks very much like the planar hole effect. It's even in magnetization, and it has this planar hole symmetry. And there is something that depends on MZ that we call the chiral torque. So again, we call it chiral because there is an MZ component. Okay? You would have only purely in-plane magnetization. This is a planar hole effect, planar hole torque. But when you take the magnetization out of plane, then you start having a Berry curvature emerging because of, well, the inversion symmetry breaking plus magnetization. And that creates chirality. So this is why we call it a chiral torque. Let's see, where are we? Ah, yeah, I should have put that before. So any questions about that now? So we'll see completely how it works, huh? Because a lot of formulas. But that, I mean, really, the take-home message of this series of lectures is really the fact that you can derive the forms of your torque and response function, anything you want, just by looking at the character table. And of course, it takes some time, but it's much, much faster and more powerful than if you actually apply the symmetry operations. So you spend time a little bit to, well, I mean, deriving that is very easy, in fact, because usually these are given to you, and you can deduce those invariants very easily. What takes a little bit of time is to make sure that this guy goes with this one, and this one goes with this one. And that takes time, but it's much, much easier than if you just do all the transformations. Just apply the transformation on your response tensor. How long do I have?
Slightly over time.
Okay. Two concrete applications of that. Why is this useful? So actually, this torque that we found explains this observation. You know, I told you that you take this crystal, you send current along different axes, and you have switching, no switching, inverse switching, and so on. And that's because of this torque. That's our interpretation at least. So if you start with a perpendicular magnetization, you see that this torque is inactive, and only those torques are. Okay? This one is inactive because you have mx on my, and if you have perpendicular, mx my is 0, so there is no 3m torque, and only damping torque and field-like torque. So you send a current, this damping torque, field-like torque, actually the damping torque, so the field-like torque doesn't do much here, just shift the energy. The field-like torque, the damping-like torque, sorry, brings the magnetization in the plane, okay? So once it is in the plane, this one is inactive, because the magnetization is in the plane. If you just do the cross product, it goes to 0. And this one becomes active. But it depends where the electric field is. You see there is the electric field and magnetization are intertwined, and in-plane magnetization are intertwined. So depending on the direction of the electric field, you're going to have, well, let's say either a positive 3m torque or no torque along certain symmetric directions, or negative torque. So then, depending on the direction, you will have positive switching or negative switching, and you don't need a field for that. So that is super nice. That is super, super nice. Okay, so then we did some DFT calculation to quantify it, and we can definitely relate the 3m torque, that's this one, with the warping. Remember, if you want to see a C3V specific property, you need to imprint the C3V symmetries on your block state. So the indicator for that is the warping of the Fermi surface. If your Fermi surface is circular, the block state that belongs to this Fermi surface, that sit on this Fermi surface, doesn't see the symmetries. But if it starts having some interesting shape here, some interesting warping, it means that the block state sitting on the Fermi surface sees the crystal symmetry, and then there's a good chance you will observe those effects. Okay. Last thing, and then it turned out that this torque, this 3M torque, exists also in iron 3, germanium 2. At least experimentally, from the theory point of view, we have done the calculation. We get a small torque. It exists. It's not very big, but you know those systems are very sensitive to the environment. So I don't. Perhaps you have some doping, or perhaps the interface plays a role. So this is interesting. We can come back on that, but there are some interesting properties belonging to this particular material. For the Jasinski-Murray interaction, what we have actually found is that, so we actually look at this iron germanium tellurium and look at the Jasinski-Murray interaction, because there were some claims that there were some skyrmions in this system. And for us, it was very, very intriguing, because there is a strong mirror symmetry in the two-dimensional plane, which kills all the Rashba effect and the Jasinski-Murray interaction that could stabilize the skyrmions. So from the symmetry perspective, there should not be skyrmions here. And still, there have been some claim that there are some skyrmions. And there are some very good reasons for that. Is because you have multi-layer, you have a gradient of composition. It's very easy to get inversion symmetry breaking when you grow those materials, just because of the composition that varies across the layers. Or just because you have an interface or something like that. But if you just take one monolayer, there is no Jasinski-Murray. Well, we did do some calculation there. So we got these symmetries that I told you about. So we got no Lifshitz invariant, so no torque, no topological texture, nothing at long range. But we did perform some generalized block theorem spin spiral dispersion. So you create a spin spiral in K-space. That's one of the three procedures I told you about. You create a spin spiral in K-space. You project it. You project the state on the you project the spin-orbit coupling on this spin spiral state, and you end up with a dispersion, and you extract the Jasinski-Murray information there. And what we found is that, of course, if you create a spin spiral that is a nail spin spiral, you don't see anything interesting. There is no asymmetry. There is no Jasinski-Murray interaction because of this mirror symmetry. But if you create an in-plane spin spiral, so short range, not long range, because long range nothing is happening. If you take a short range spin spiral, you do have a strong Jasinski-Murray interaction that actually stabilizes this kind of in-plane spin spiral along low symmetry directions. So this analysis is very important. Okay, I will stop here. I will take advantage of this school to advertise for positions. We have 2 PhD positions and 2 postdoc positions that are open on various topics. So if you have friends who are looking for PhD positions, or if you're looking for a postdoc, please contact me. Thank you very much.
So can we apply this formalism to anti-Fermat?
Yeah.
Tools in some way.
So that is a very good question. I would say yes, of course. Now the question is how. So you can. So in antiferromagnets, what you need is to determine what is the symmetry of your nail vector. Okay, because the way you would do that, you would say, I expand my response function in terms of either MA plus MB. Let's take a collinear one. It's simpler. But the same principle applies if you have more. So I expand it in MA and MB, or in the nail vector and the total magnetization. So the total magnetization is a magnetization, the next vector is fine. The question is, how does the nail vector transform, right? Because if you exchange A and B, the nail vector changes sign. So you have to be a bit careful for that. We haven't done it. You have to be a little bit careful with that. It's actually something we're discussing with Jakub. This school is so rich. Came with a lot of new ideas. So I think you can do that.